All right, we're recording. Welcome to exam day, our final class day. Your exam is on Thursday. And I'm not going to hold Zoom hours while an exam is in progress. So I will absolutely be available over WebAssign. Everybody's home now. Everybody's safe. I have my eyes on her even as we speak. And so I will be answering WebAssign like throughout the day, every day until next Friday. I'll be working every day, but so I'll be there for you guys. All right, so let's get to this review. And not enough people yet. I don't want to see me. I am going to open the chat just so I can see everyone down here. It'll come back time and again. Every once in a while I have this open, I'll be looking for thumbs up if you're good, just, you know, those easy nonverbal cues or verbal, whatever, okay. Let's look at our exam 3. Let's make that go away. And at times I'll make that go away. All right, so Desmos Scientific Calculator. There's also a formula sheet. And I'm going to check and make sure on your exam 3 folder in Blackboard. I'm going to see if this formula sheet is in there. If it is, you should use it. If it's not, I'm going to make sure it's posted. It's just one page, just like our other ones. This is a great formula sheet to remind you of some of the formulas. So I'll be popping back and forth, showing you various places where we might look for these. Here's the review. You also have the Desmos calculator if you need it. So remember, this is chapters 7 and 8 only. So list the elements of the set. The set of outcomes, I'll make it big when we can. When we need paper to work it out, we'll use it. A set of outcomes of tossing 3 distinguishable coins or 3 indistinguishable coins. Now, when it comes to coins, I'm going to take my shortcut again. Feel free to have access to one of these tables where I called it something fancy like dice, coins, cards. Right, this will be our table of indistinguishable. I'm going to redo this so that there are colors on the top row, colors on the top row, first column. Woo, different colors, so we can see how the different colors match up. But here we can see that there are 6 times 6 or 36 outcomes when it comes to rolling 2 distinguishable dice. Notice 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Never will a die, a 6-sided die, have a 7 in it. So as we're looking at our possible answers, let's go ahead and just make this big. Why am I looking at dice when we're talking about coins? 3 distinguishable coins. My goodness, people, I can't even read my own, listen to my own reading. Today should be awesome. 3 coins. So heads or tails for each of them, right? And there are 3 of them, 2 options. 3 times equals 8 outcomes. And we know what those 8 outcomes are. They're actually on this sheet as well. Down here, here's the results of flipping 3 distinguishable coins and noting the side face up. So I accidentally went to the right table, just used the wrong part of it. And we see there's 3 H's and so on. So I'm going to copy this by hand onto here. The sample space is 3 H's. I cannot talk and write these at the same time. I'm not that talented. And I know I wasn't actually looking. Okay, so Here we come back as we look at our note paper. Distinguishable coins, it's going to be this one. 1, 2, 3, 4, 5, 6, 7, and there's an 8th one here. So we'll choose this outcome. However, if they're indistinguishable, if we cannot tell them apart, then really what we have is I'm going to call this indistinguishable. We have 3 heads, or we have 2 heads and 1 tail. 2 heads and 1 tail. Those 3 are all the same. We might have, let's see, 3 heads, 2 heads, 1 head. So that's 2 tails, 2 tails, 2 tails, or we'll have no heads. So I think of this as 3 heads, 2 heads, 1 head, no heads, because they're indistinguishable. We don't know, they're all a 1976 quarter, and you can't tell them apart. So indistinguishable will only have these 4 outcomes here, where we have 3 heads, 2 heads, 1 head, and 0 heads. So that's the difference between distinguishable and indistinguishable, and I'm going to get some points in my review by submitting these answers. All right. And remember, this is kind of bouncing around. There are 20 questions on the review. There's only 15 on the exam. So if you do well at this review and you seem to understand what we're going through here, you're going to be just fine. Use an annoying green as the line in between. All right, so number 2, the number in A is 44, the number in B is 17, the number in the intersection is 5. This looks like something I've seen before. I'm going to pull out my formula sheet. It's talking about the number. Oh, this is where we first start seeing numbers, and here's the union rule of counting, which is ugly like that. So I'm going to write it down on my paper. It says the number in the union is the number in A plus the number in B minus the number in the intersection, because we've used it twice, once with A and once with B. So we go back to our problem, all right, once we find that formula, we substitute what we know. We know the number in A is 44. The number in B is 17. The number in the intersection is 5. And this becomes a simple arithmetic problem. It looks like we're going to get, okay, so I do 17 minus 5 first. I buck the trends. 12 and 44 makes 56. Remember, have this handout ready so that you can, look up formulas if you don't remember them, or go through and write the formulas down for yourself. All right, let's do one more, and then I'm going to ask if there are any questions. Really? Really? Okay. Here we go. Number 3. Number 3, use the given information to complete the solution of the partially solved Venn diagram. So as I'm looking at this, I see circle B is missing one number. So I'm going to start there. Okay, so in my circle for B, I'm missing one number, and I see that the total number in B should be 10. I currently have a box plus 1 plus 5 plus 0. So box plus 6 equals 10. My box must be 4. Okay. And I have not done it like this in class before. I really just kind of did it right now because All right, let's throw down some orange here. What else? Now, circle A is missing one value. And circle C also. So the number in A is supposed to be 15. Currently in A, I have 10 plus 4 plus 1 plus the box. That tells me I already have 15 and my box must be 0. My Chihuahua thinks that we should just cuddle on the couch all day, just sit, so she has somebody warm to sit next to. If you have a Chihuahua, you know. They're the most devilish dogs out there, but I would not trade her for anything. All right, I want a Chihuahua ranch, like fields of Chihuahuas just running free. N of C equals 30. Currently, we have 10 and 4 and 5 and a box. So that's 19 plus the box to get 30. 30 minus 19 is 11. So my box must be worth 11. And we're almost finished, but we see this box out here. We have to have an answer in there. So I ask myself, well, okay, the number in C, nope, the number in sample space, number in the sample space is 39. So I'm going to add up all the other numbers, and I just kind of work my way box by box and fill in as I can. And I always start with what's missing 1, okay, what's next? What's missing 1, okay, take the next one. So currently I have 0, 1, and 0 across the top, 10, 4, and 5, and 11. And there's a box on the outside, and this whole thing has to add up to 39. Now we know that this is 9. 9 and 1 makes 10. 10 and 10 makes 20. That's 31. Plus the box. Feel free to use your calculator. Always use your calculator to check my work. You've seen the arithmetic before. When we subtract, the box equals 8, and then we'll fingers crossed it, hit enter, and hope. Oh, look, now I don't have to see myself even better. Any questions on that particular problem? Let me throw this up here and this over there. We good? All right, fantastic. Awesome, we're saving too. I'm never gonna lose class material again, I swear. All right, let's take this back down a little bit. I'm gonna need to see these together, or at the very least, up over there. Let's copy it over onto here. We don't want to do any of that calculus nonsense. Here we go. And now we can see this on a good size. Multiple choice test, you know, it's always everybody's favorite. Sarcasm intended. Professor Easy's final exam has 9 true-false questions. So just looking at true-false, we have 2 options. And we have 9 questions. So we have 2 options 9 times. So that's 2 to the 9th possibilities. Followed by is going to tell us that we multiply. Two multiple choice questions. So our multiple choice, 2 questions. And in each multiple choice question, you must select the correct answer from a list of 4. So these are our options. Multiple choice has 4 options each. There are 2 questions. So this is 4 to the power of 2. And when I multiply 2 to the 9th times 4 to the power of 2, I'm going to use a calculator. Again, we don't need to see any calculus. 2 to the 9th. I'm going to come out of the exponent before I hit times 4 squared. Always remember, like, pay attention to your display up here. We can't just go typing along, especially if you're using exponents. There should be 8,192 different exams of possible, right? And we know that later on, this is going to end up being our denominator for perfect scores and things like that. All right, so I think the answer is 8192. Remember, these are pools of questions, so you might get a problem that's slightly different, but it has the same idea. So it might not be exactly this, but it'll be similar to this. You might have different number of options on the multiple choice. You might have a different number of questions for the truth. You know, it just all kind of goes here and there as needed. All right. We're on number 5. How many ordered sequences? So as soon as I see ordered, I'm thinking permutation. Permutations are races. It's where order matters. First place is different from second place is different from third place. We're not looking at a committee. Contain 5 objects chosen from 13. So I ask myself, how many do I have? I have 13. How many do I want? I want 5. So I'm looking for the permutations of 13, choose 5, which is 13 factorial divided by 13 minus 5 factorial. And what is that? 13, 12, 11, 10, 9 times 8 factorial over 8 factorial. Let's use a super tiny red one. And we can multiply this out. I'm not going to do that in my head because that would hurt. My brain's liable to explode. But we could do 13 math button over the probability and PR, and then 5, right? And we've seen how to do this on various calculators. 154, 440. And for some reason I didn't change color, but that's all right. I'm okay with that. All right, so what I'm going to do is I'm going to stop putting these in. Not because I'm afraid I'm going to get the rest of the answers wrong, just because that's taking up too much time. I'm looking at our time here. We're already 20 minutes in. We're averaging about 4 minutes per problem as we're talking about them. I forget every once in a while. Are we doing all right? I forget to check in. Is there anything in the first 5 problems that any of you would like for me to go back to? Yeah, I don't have the chat up. Let me see if I can bring that back. All right, Nadia, you have your hand up. We good? Was that a we good, or is that a we have questions?
I was gonna ask if you were gonna go over the last four because I didn't understand how to do those.
You want me to switch it around and go 20 and work our way back?
Wait,
Oh,
Like I can start
I
at the
thought-
bottom and work our way back.
wait, no, wait. Quick question. Could you go over number 7 actually really quick? Like the second part of it.
Number 7?
Yeah,
Okay,
the second
yeah,
part.
absolutely, absolutely. All right, I'm going to start skipping a little bit here and there. We've had this question. We know this question. Your international diplomacy trip, it's not one of the harder ones. I'm going to put the chat down again. Yeah, we'll keep going. I'll make sure we get through the entire thing. That's what I'll promise you. So I'll just start writing some notes instead of I'll start writing some notes instead of doing the full problem. Your international diplomacy trip requires stops in Thailand, Singapore, Hong Kong, Laos, and Bali. How many possible itineraries in which the last stop is Thailand? So Thailand, Singapore, Hong Kong, Laos, and Bali. 1, 2, 3, 4, 5. 5 stops. So 1, 2, 3, 4, and I want to end in Thailand. So I have these other 4 options as my first step, 3 options as my second, 2 options as my third, 1 option before I hit Thailand, and this looks like it will be, it's an and then, so we multiply it. 12 times 2 is 24. Now, it changes based on, depending on how many they tell us that we have to start with or end with, or how many stops there are in between. Number 7. All right, suppose 2 dice, 1 red, 1 green are rolled. Consider the following events. Yeah, you guys seem to be really good about figuring out these intersections and unions, which is terrific. But it's always the counting of them, like it's hard to see sometimes. So the red die shows a 4 is A. And numbers add to 7. Numbers add to 7 is B. So this is a straight up A intersect B. But what's in that? The actual question that was asked is, hey, how do we do the second part? Okay, so if the red die shows a 4, let's take this back to red. The red die shows a 4, and the numbers add to 7. Tells me the green die has to be a 3. And I don't think there's anything else in which the red die shows a 4 and the numbers also add to 7. There's only one element in this particular one. So I would write down all the times that the red die shows a 4. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. Hurts my head. So our green could be a 1, 2, 3, 4, 5, or 6. How many of those also add to 7? That adds to 5, 6, that adds to 7, 8, 9, 10. There's only this one. And that might be the better way of going about it, is to actually write out all of element A. And then out of those, pick which ones fit in B also. All right. I try to avoid red and green because it's so, I don't know, it just screams Christmas to me. And they're kind of both annoying colors, like with stoplights and things like that. But, you know, whatever. One design likes red and green. Number 8. Okay, so everybody's table is slightly different. What's being asked is always slightly different. It comes down to reading. Just it's the exact same problem as this, only we're going backwards. E union F. So E saw an increase in housing prices of 4% or 5% or more. Union. Basically, we're asking, is union or is union and we know that union is or, right? A union, like the union of marriage, it's all your stuff, all their stuff, and the stuff you got together. So it's the union, the joining. And is that first date material, the stuff that's only safe to talk about on a first date, unless you want to make them mad. So all the outcomes. So I'm listing everything that has 5% or more. So we have Pacific, we have Mountain, we have West, South, Central, South Atlantic. Or, so we add to that F, East Coast, so we'll add the New England and Mid-Atlantic states. So it looks like it'll be this one, all of them. But what's the intersection? The intersection is above 5% and on the East Coast. So South Atlantic would be the only thing there. And list the outcomes. And so it's the same thing looking at union versus looking at intersection. And the key is, remember, union is or, intersection is always and. It's a joining. All right. Well, everybody loves the authors. How sick of your authors. Bring it back to some standard colors here. Black, blue, purple. Describe the events. So 7, 8, and 9 are all the exact same problem, just coming at you from different kind of orders. So the intersection, right? This is a great thing to have on a note card. The intersection is the event that the author is, intersect and, successful and new, right? Make sure you know what the letters stand for. Union will have or, right? That's the only difference. That's what we're looking at here. Remember when we're looking at the intersection, I'm going to take this table, pop it up over here, or down there, wherever. If I'm looking at successful and new, when I count all the successful and get 18, and I count all the new, notice this part right here. Let's go back to yellow. The 16 is counted twice. This is our intersection. That's where they overlap. That's where my circles overlap. It'd be like the letter they share in a crossword puzzle. So I can answer both of these questions really quite easily. The intersection is 16. The union is I'm taking that 18, right? All of them that are successful and all of them that are new, but I'm going to take out that 16 that I double counted. This is the union rule of counting. We had it in number 2. An alternative, I'm not going to call that or, you could add up all 3 areas here and get 3 and 16 and 2 which is going to be the same total. 19 minus 16 is 3, 18 and 3 is 21, 16, 17, 18, 19, 20, 21. So you could look at it either way, either using the union rule of counting or just counting up the bits that make it up, because we don't ever want to use the totals and the little parts in between in the same method. All right. We're getting there, we're getting there. What was that? That was number 9. Yep, I said number 9 up above. Okay, we are almost halfway through the exam and we're 30 minutes into the review time. So that's good. You're gonna have plenty of time with this 2 hours. I think most of you will find that this exam is the one that you do the best on, because it's the newest stuff, but you've most recently learned it. And you've had so much work on the same things over and over again, right? The following table shows the results of a survey of 400 authors. Compute the relative frequency. An established author, that will be our denominator. And then of the established, I want successful. This will be our numerator, but in this particular, my goodness, I've lost words, folks. An established author, there are 296 authors, established authors. 296 established authors. How many of those established authors are successful? 112 of them. Because I'm only looking at the successful authors that are also established. This is established intersected with successful. And the number of established is 296. The weighting of the die, 8 times as likely for a 5 or a 6. So if I go old school on it, if I go totally old school on this, 8 times as likely. So we have 1, 2, 3, 4, a 5 could come up 8 times. And a 6 could come up 8 times. So that's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there are 20 outcomes. For a 1, there's only 1 out of 20. For a 2, there's only 1 out of 20. We did a step-by-step, you can't skip steps tutorial on this. For the 5, there are 8 out of 20, right? There are 8 of these. And we should simplify that fraction. That's 4/10 or 2/5. And same for 6. But remember, these all add up to be 20, right? This has to add up to be 20 out of 20. 8 and 8 is 16, 17, 18, 19, 20. So we have all of our little boxes taken care of. If I want to look at even numbers, the probability of rolling an even number, let's put these in boxes. If I'm looking just at even numbers, I have 1 out of 20 and 1 out of 20 and 8 out of 20, 8, 9, 10. And it makes sense. I don't know why I took that step down when 1/2 is easy. Right, the 1 and 2, 3 and 4, 5 and 6, they're kind of all offset. So it's still a 50% chance of rolling an even value. All right. Number 12 uses the union rule of probability. You know how to do the union rule of probability because it's right here. And you know how to follow formulas because you've done it before in the counting, right? The chapter 7 stuff we did. All right, let's talk about cats. This is like the monkey sitting at a typewriter and the first 24 things they strike, same idea. A standard piano keyboard has 88 different keys. Find the probability that a cat jumping on 4 keys in sequence and at random, possibly with repetition, so they might step on the same one twice, will strike the first 4 notes of Beethoven's symphony. Ba, 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 ba. All right. Oh, yeah, not in tune whatsoever. So there are 88 keys. The first 4 notes is what the cat is jumping on, but only one of those is Beethoven's 5th, right? The first 4 notes of Beethoven's 5th. So that's why they want you to leave the formula instead of writing it out. 1, that is desired outcome. And 88 to the 4th possible outcomes. Because we all know that the probability is the total number of desired outcomes divided by the total number of possible outcomes. And then we leave it. Right? Don't let this one be difficult. Write it down exactly what it says. And remember, probabilities are always going to be fractions or decimals between 0 and 1. Number 14 is the conditional probability. And maybe you have that formula memorized, maybe you don't, but it's on the formula sheet. All right, if it's on the formula sheet, we can work it out. Because we are given the probability of B is 0.5. The probability of the intersection is 0.2. I want to find probability of A given B. Fantastic. This, it turns out to be 0.2 over 0.5, which is 2/5. And if you prefer, you could write that as a decimal. Just use your formulas. You know how to use formulas. You're actually really good at it because you're really good math students. You might not want to do math as a career or anything, and that's why you're in this class instead of my calculus class, but I'm hoping to see some of you in my calculus class someday. Let me slow down on these ones because these are the ones that more people have questions on. Number 15. Find the conditional probability, all right? So I'm already thinking this formula, conditional probability, 2 fair dice, 1 red and 1 green. The red one is 2, given green is 2. So I'm going to let A be the event that the red die shows a 2. B is the event that the green die shows a 2. Because whatever is given, right, that comes after the line. So this is A given B. If I could rewrite my statements in terms of A and B, now I can find the probabilities of these. And I am going to go back to the red and green die. Okay. So the red die shows a 2. Red die shows a 2, so we'll have 2 6 times. And with that 2, we could have a green 1, a 2, a 3, a 4, a 5, or a 6. And I really wish this could be just a regular old pen or whatever. Okay. Now our green die shows a 2. Means the red die could be a 1, a 2, a 3, a 4, a 5, or a 6. I'm not putting parentheses around that. Now we know that all of these, there's a total of 26. 26 total possibilities. 26, whatever. Jeez. Okay, 36 outcomes. We need the probability of A given B is the probability of A intersect B divided by the probability of B. So A intersect B. Where is the red die 2 and the green die 2? It only happens once. It happens to be their overlap. That's one time out of 36. Probability of B, the green die shows a 2, 1, 2, 3, 4, 5, 6 times. 6 times out of the 36 possible ways that we could roll these two dice. All right, so if we divide by a fraction, we multiply by the reciprocal, the 36's cancel out, and we'll have an answer of 1/6. All right, so we'll end up with 1/6. And I swear I've done this problem about 5 different times now. If you get lost and you get confused, guess 1/6. It happens way more frequently than is coincidence. There might be a programming issue here where there was some favoritism. I don't know, maybe not. Maybe if you guess 1/6, then it's wrong, you'll hate me, but we'll both get over it. How we doing? You doing all right? Thank you. All right. All right, appreciate the feedback. Thank you very much. All right, number 16. This is where I need to slow down. Okay. List the elements of the given set. Are you kidding me? Okay, set of all outcomes of tossing a coin 5 times. It's the same coin, we're tossing it 5 times. This will be distinguishable. Because you're doing it 5 separate times. It's not like we're flipping 5 coins at once. Those might be indistinguishable, but you have attempt 1, attempt 2, so they're separate. This is distinguishable. Heads or tails, 5 times, 2 to the 5th, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. There are 32 outcomes. And I'm looking over here. That's 1, that's 4, that's whatever. I'm going to go with that answer. Because I know how many, I can look at my list and think, yeah, that's probably pretty close to 32. I'm going to assume it's close to 32. All right, number 17. Consider a bag containing 5 red, 2 green, 1 transparent, 4 yellow, and 2 orange marbles. That looks like 5, 6, 7, 8, 12, 14 total marbles. how many possible sets of 5 marbles? All right, so sets of 5 marbles in which all are red or green. Oh my goodness. Okay. How many sets? So we're not looking for a probability. Sets tells us we're going to use combinations. There's no order. It's not ordered sets, it's just sets. So we want 5, and we have 14. So here's the deal. All are either red or green. So I could have 5 red, 0 green, or I could have 4 red, 1 green, or I could have 3 red, 2 green. Right? And that's the most I could go because that accounts for all the green. So the way we'll do this is going back to this whole red and green, get new colors. Okay. Out of the 5 red that we have, we want all 5. Out of the 2 green we have, we want 0. And then what about the other marbles that are not red and green? We have 4, 5, 6, 7 marbles remaining. We want none of them. Or add. And then we'll do it all again. We want 4 red. So out of the 5 red we have, we want 4. Out of the 2 green we have, we want 1. And out of the 7 marbles that are not red or green, we want 0. Or, so that goes up in that spot, but I knew I wasn't going to have enough room. Out of the 5 red we have, we want 3. And out of the 2 greens, we want 2. And then out of the 7 marbles we have left, we want 0. So I'm going to make this a big page so that we can find all of these values. And we're going to use a calculator to do this because we are not trusting my brain right now. Here's a little reminder. Put it in purple. A couple of things we know. C of n comma n is 1, as is C of n comma 0. C of n comma 1 is n, as is C of n comma n minus 1. So some of these will come in handy. This formula will come in handy a couple of times because here we see we have 5 comma 5. This will give us a 1. 5 comma 5. And then 2 comma 0 will give us a 1. And the 7 comma 0 will also give us a 1. I couldn't see black all of a sudden. Plus this 5 comma 4, right? That's n and 1 less. So this happens in 5 ways. 2, but I only want 1. So this will be a times 2. And you can verify all of these on your calculator. I'm just too lazy to show all the button pushing for it. Now 5 comma 3, I'm actually going to find that on the calculator because it's not one of these little cheaters methods, ones that I have memorized. I will go with a 5 math over to probability. I'm using the C combinations and I want 3 of them. So that's 10. 2 comma 2, since it's n comma n, this is a 1. And I don't want any translucent yellow or orange marbles. So that one turns out to always be a 1. When I multiply, I'll get 1 plus 10 plus 10, 1, 10 plus 10. 21 sets that are either all red or all green. I'm going to cross my fingers and hope that's the right answer. I'm going to take a minute to put this one in. I'm going to cross my fingers. Oh, so thankful. So thankful. All right. Is that helpful for those of you that were struggling a bit on that one? Yeah, you're still writing. I know. The key here is sets of 5 in which all of them are red or green. And we have to write it out mathematically. What does that mean? All red or all green? Go ahead, Nadia. What's your question?
It's because mine, the question that I have on my exam review says how many sets of 5 marbles do not include all the red ones. So I don't know like how to work that.
Would that change, right?
Mm-hmm.
Do not include. Wait, okay, say that again.
It says how many sets of 5 marbles do not include all the red ones.
Okay. There's a couple of ways we could go about this. I'm going to use my same numbers just to show you how we could do it. This is the exact opposite of sets that have all the red. Nope. Nope. I don't want to give it to you that way. That's going to be horrible. That's going to be way too much explaining. We're going to do it like this. Sets of 5 that do not include all the red. So it could have 4 red, 1 other, or it could have 3 red, 2 others, or it could have 2 red, 3 others, do not include all the red. Or 3, oh, we have 5 reds. Oh, we don't want all the red though. We don't want that one. So it could be 4 red, 1 other, 3 red, 2 others, 2 red, 3 others, 1 red, 4 others, or no reds, 5 others. And we would do it exactly like we did here where we have 5 reds. We want 4. We had 14 total marbles. If 5 of them are red, then 9 of them are not. We have 5 red, we want 3. But we have to make sure we take into account all 14 of those marbles. 9 and 5 makes 14. 2 of them here because we want a total of 5. So we always have to make sure, and here we did it too, 5 and 2 and 7 makes 14. 5, 0, 0 makes 5. Every single time, the second numbers always add to 5. The first numbers always add to 14 in their set because I have 14 total and I want 5. And so it would keep going like this. Does that make sense, Nadia?
Yeah, but how did you, why did you put the 9, the combination, the 9, 1?
Oh, we have 9 others.
Mm-hmm.
Nope. We're back to the table that I don't know.
And it's always C of have and want. because we still have to choose one more to go with the 4 reds. We always have to have a set of 5. So 4 of the reds is okay because it's not all the reds. So if I have 4 reds, I need 1 other. And so I'll use 9, 1 because we have 9 that are not red. I want 1 of them. And then we have 9 that are not red, and I want 2 of them because I'm taking fewer reds each time.
Okay, so if my marbles were a total of 13, I would have put 13.
You use,
Then the
it depends on your red. This is the total minus how many reds you have.
oh, okay.
There we go. How many of you are in the library? That'd be hilarious if you were all just like sitting together hearing the same thing. I'm guessing no, but okay, let's go to the next problem. Oh, let's not go to the next problem. Okay, we're good, we're good. 4 coins are tossed. It doesn't say distinguishable or indistinguishable, so we are going to assume distinguishable. 4 coins are tossed. There's 2 options for each coin. 4 coins, 2 to the 4th is 16 outcomes. Right? Number of options at each step. There's 2 options for each coin, heads or tails. Total number of times is in the exponent, 4 coins, so 4 times. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All of them. There's only 16 of them there, so you're going to hit all of them. Four coins. 4, 2 heads or tails, 4 coins. And so it'd be all of these. Compute the probability of E. Fewer tails than heads. I'm going to use this to count fewer tails than heads. That has fewer tails. That's equal. That has fewer tails. Fewer tails. Fewer tails. 1, 2, 3, 4 out of 16. And of course, we would reduce that down to a quarter. And I didn't get the problem right because I didn't mark all of these. Oh, so now all of a sudden they're distinguishable? Oh, 2 of you got questions because I'm doing it wrong. All right, talk to me.
Okay, for I guess our number 18 is completely different because it's saying that consider the given event, a die is weighted so that each number is half likely to come up to either 1 or 6.
I got you. I'm gonna open up yours, Esther, but I'm not gonna show everybody your grade. You like how I remembered that first?
Okay.
I think I've showed your grade enough to the whole class, and we're recording this time, so. Oh yeah, an A. There we go. Of course, it's going to show your problems, so you'll still see your grade. Okay. And you'll also see the correct answers. All right. Number 18. So we don't have to see any incorrect answers. It's all good. She has a question on it. We haven't started it yet. A die is weighted so that each of 2, 3, 4, and 5 is half as likely to come up as either 1 or 6. Oh my goodness. You want to know the secret? 16 through 20 are the questions that are not on the exam.
I don't know if I can trust that.
What's that?
I don't know if I can trust that because I know
No.
last time because every time you say 16 through 20 are never on the exam, and then all of a sudden some random question pops up, and I'm like, I don't know what to do.
Okay. We'll do it. Let me copy this problem over. All right, we could do this. We could totally do this. Here, over here. All right, let's do this problem. A die is weighted so that each of, okay, so first thing I'm going to do is I'm going to make a probability distribution table. And down here, not in red, I'm going to put the probability. Now, 2, 3, 4, and 5 are half as likely. So if these are each once, then the other ones will happen twice. Right? Because 1 and 6 come up 2 times as more. If 2, 3, 4, and 5 are half as likely, then 1 or 6 are twice as likely. So 2, 3, 4, 5, 6, 7, 8 is our total. This is 2 eighths. This is 1 eighth, 1 eighth, 1 eighth, 1 eighth, and 2 eighths. All right, so half as likely if I make them 1, then these other 2 will be double. So how many elements in the sample space? There's only 6 elements because there's only 6 things that I can roll. This part is our event, right? Always after the semicolon. A 3 comes up. So 3 is the only possible thing that we want for our event. But to find the probability, that's where our table comes in. I'm going to stop it here. And that's why our probability is 1/8. All right, so, and it all comes up from setting up this probability distribution table first. So what I'm going to do is I'm going to look at Nadia's version of the same question and see if it's the exact same one. So I'm going to stop.
Yeah, it's different. Mine's different also. Yeah.
Good question. How did you get the 8 from as the total? Did you like add up like 1, 2, 3, 4, 5, 6?
But I added the numbers above because 1 can happen 2 times for every 1 time each of these happen. I get 2, 3, 4, 5, 6, 7, 8.
Oh, okay.
So it's up here in the weighting. That says weight, but you can't see it. All right, I'm going to not show anybody's grade so that I could actually share the recording. I could do this quickly. I promise. Right here it is. All right. I'm going to copy this over and put it on the paper, even though she's made a valiant attempt. You're close. Here's your answers. Okay, so the same idea. What are we doing here? 2 indistinguishable dice are rolled. So when we look at that, no, because you guys can't see it yet. I'm getting better. All right, so this is the screen that we're actually looking at. When 2 indistinguishable dice are rolled, what can happen is 1, 1, 1, 2, 1, 3. And then it's on this diagonal. Because, and it's good, I use black anyway. Over here would be a 2 and a 1, but 2 and 1 is the exact same as 1 and 2. So it's only these ones, and that's why there's a total of 21 outcomes. So the numbers spacing add to 7, since I already have these, I have a 7 here and here and here. 7 is on my diagonal. There are 3 of them. Excellent. Compute the probability of E. The probability of E, there are 3 out of the total of 21. How is that possibly 1/6? Because I get 1/7. Did I miss a 7? I didn't. That's 1/7 all day, folks. 21 divided by 3, right? I mean, look, they guessed 1/6 also, and it's wrong. It even shows you here 3 divided by 21. This is an incorrect answer. But, you know, when in doubt, answer 1/6 for that one. That's frustrating. I'll give them a notice that I think that answer is wrong. And we'll see what they say. But it's not going to help you guys in time because this is due tomorrow. All right. Questions on this one? Yeah, I can look. All right, Esther, question.
Okay, so I noticed that we all have different problems. Is it like based off of our, like how our test is going to be like structured, or it's just random?
Random. It's set up so for problem number 1, you could get any of 4 problems. So some people get, like you might get this one on the review, but this one on the exam. But this might be a problem somebody else had on review, but they get your problem on the, it's all random. There is absolutely no way for me to control that or anyone else.
Okay, thank you.
You're welcome. I know that's not awesome news. 19. Oh, I like this one. Okay, good. Number 19, my version of number 19 anyway. There are 40 students in categories A and B combined. All right, so combined means a union. Some students are in both. 26 are in A, 26 are in B. E is the event that a randomly selected student among the 40 is in both categories. All right, so I know there's a total of 40, so I'm thinking Venn diagram comes to mind right away because, you know, I don't know, it just comes into my head. I need to find out what's in this intersection. That's what I'm really looking for. And I know that 26 plus 26 makes 52. But how can I have 52 if there's only a total? So it must be 12 overlap. I'm going to say overcounted. Because 52 minus 40 is 12 overcounted. And if 12 is overcounted, the probability of our intersection is 12 out of 40. And that's how they get the answer of 0.3. Oh, look at this. I'm still using not is. What? Compute the relative frequency. 2 heads. Okay. I'm going to do another 19. Because it's slightly different. There we go. 2 coins are tossed 40 times. Two heads comes up 11 times. So 11 out of those 40. So what I want to know is event E is at least one tail. So that is tails, 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 heads, heads, tails. But keep in mind, when you're flipping two coins, either heads, heads, or these three are the total number of possibilities. So the probability of event E is 1 minus 11 over 40, because it's the opposite, right? 11 times heads, heads has come up. What's the probability that that doesn't happen? That's our complement event. To rewrite 1, we write it with our common denominator is 40 over 40. When we subtract fractions, we get the common denominator, and then we just subtract our numerators. 40 minus 10 is 30 if I take away one more. And that's how I get 29 over 49, or excuse me, 29 over 40 for my answer. But I'm not going to waste time putting that in. Class is almost over. All right. So this whole idea of E is the complement to the set HH. So probability of E is 1 minus the probability of heads, heads. And that's how I got that formula. Number 20. I was definitely going to hit number 20 because I've seen several people have problems on just the second half of this particular question. So we have 2 dice, 1 green, 1 yellow. I will not write in yellow and hurt your eyes. Those are rolled. I want to find the conditional probability. So I know that the number in the sample space, there are 36 outcomes possible. Dice have 6 sides. They are distinguishable. So there are 36 total outcomes. So I'm looking at the sum is 7 given green is not 3 and yellow is 3. Oh my goodness. So A is going to be the sum is 7. And B is green is not 3 and yellow is 3. Oh, my words killing me here. So the probability of A intersect B. Probability of A intersect B. A sum of 7 where the green one is not 3. So we're going to do green, comma, yellow when I write these. The sum of 7. To get a sum of 7, we will have a 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. Okay, green, yellow, green, yellow, green, yellow. Given the green is not a 3, so I'm not using that one, and the yellow is a 3. So there's only one time the probability of A intersect B is 1 out of those 36. So how many times will we have a green not a 3, but the yellow is a 3? Well, oh my goodness. Stupid. Okay, it's not stupid. I'm not recording this. I'm totally recording, it's not stupid. The green one is not a 3. So that is 30 possibilities. that green is not 3. But it's an and. So out of those 30 possibilities, and I need to bring up this sheet because it's killing me here. I'll bring it down a minute. So we're going to let the green one be this row. All right, so no, let's make it the column. Okay, this row. This row, green cannot be that one. All right, so we can't use this row, but we use the 6 here, the 6 here, the 6 here, here, and here. But also, so excluding this row, I must make sure that the yellow one is a 3. So the only possibility, so I don't need to look at those 30, it's an intersection, it's an and. The only times where the green one is not 3 and the yellow one is 3 is right here. We're looking at 1, 3, 2, 3, not 3, 3, because the green can't be 3, 4, 3, 5, 3, and 6, 3. All right, the green one is not a 3, but the yellow one is a 3. It's 1, 2, 3, 4, 5 of those. So the probability of A given B is the probability of the intersection divided by the probability of B, which is 1/36 divided by 5/36, which is 1/5. Oh, do not please be done. There's a reason we give you 2 hours for this exam and not 1 class hour. Because it's impossible to do all these in that amount of time. Now, here's the question. Say whether the indicated pair of events is independent. Are they independent? How do we know this? On our formula sheet, we see that the events are independent if the probability of A intersect B, which we have here, A intersect B is 1 out of 36. Does that equal the probability of A times the probability of B? No, it does not. The probability that the sum is 7, there are 1, 2, 3, 4, 5, 6 of those possibilities, 6 out of 36 times 5 out of 36. It doesn't equal the intersection, right? So probability of A times probability of B does not equal the intersection. So these two are dependent. They definitely depend on each other in order to make things happen. And I went to my formula sheet that I'm going to make sure is posted in your week 15 folder on Blackboard exam 3 stuff. All right, use that formula right there. My goodness. I'm exhausted. I'm going to say a couple things about the final exam. Here's what I'm going to do for you. I am going to, I'm going to share my screen again because, you know, I keep going back and forth on that idea. Yeah, move. Let's look at this. Let's look at mine. I am going to go to my home. Let's see where my home takes me. If I go to past assignments and say I want to look at exam 1, I could click on exam 1. The password is ready. I know you wish you had all those. The password is ready, and I can launch assignment. You can go back to any of your exams and I'll do this, but notice it'll say past due. You cannot. The due date for this assignment is past. You can view your work, but no changes can be made. You will not get an extension. Don't even bother asking. But you can view the answer key. And so when you're reviewing for the final exam, do the final exam review. If you feel you need more preparation, go back and look at exam 1, exam 2, and exam 3 reviews. I'm going to extend exam 1 and exam 2 reviews for you. And if you still feel like you need more because you're freaking out and you don't want to, you maybe missed an exam and you want your final exam to be your highest possible score, come back in and look at exam 1 and exam 2 and view the answer key. And starting on Friday, you could view the answer key for exam 3. So always come back and review your past work. You can see I got a really bad score on this exam. I can't improve my score, but I can look at the answer key
Ms.
and
Johnson,
work through it and make sure it's all good. Yes, ma'am.
did you say that after our final exam, like based off if we do good on the final, then you could like use that score to replace like a low test score, or
Absolutely.
either if we do low, then you were going to take one of our test scores and replace it with the final one?
Let's say, for example, all right, suppose you have exam 1, exam 2, exam 3. Let's suppose somebody missed that exam, they have an 82 and they have, oh, we haven't taken exam 3, so you got 100. And then you take the final and you get, I don't know, maybe an 89. What I'll do then is I'll take out the 0 and put in an 89. And then I'll calculate your course average. However, if you have, say, a 95, 100, a 98, and a 75, because you're just jacking around in your final because you're over it, it just stays like that. I don't replace anything, nothing changes.
Okay, thank you.
You're welcome. And the last situation is, even if you don't have a 0, even if this was an 80, if this was an 80, I'd still take the final exam and replace it and give you a few more points. So that's how it works out with the final and replacement of grades. And that happens by hand. I have to do that myself. So that's not going to happen immediately after you take the final. It'll happen by Thursday of final exam week. All right, any other questions? Yes, Nadia.
I have a question about the last question on the exam review. It's because mine says the sum is 3, given that the dice do not have the same parity. And I don't know what that means, the
Okay.
dice thing.
Parity means even and odd. So if one's even, the other one cannot be even. Or same parity, either they're both even or they're both odd. So like 1 3 1 5 1 7 1 1 1 3 1 5, same parity. 2 2 2 4 2 6, the same parity. So then you'll just look at your table and you'll see like rows of evens and things like that. Because we're after class time, I don't have time to
removal, but otherwise.
We're about to finish.
So when they don't have the same parity, it's because they're one of them is like even and the other one's odd.
Perfect.
Okay.
Sure, I'll kill you.
Perfect. Angela, do you have any questions? All right, I'm going to end class now. Remember, Thursday is your exam. I'm going to be updating Blackboard. I'll send out another announcement. Maybe I'll just post it in the folder to let you know what all I've opened up for you. Thank you for joining me. Thank you for being understanding. Thank you for an amazing semester. I look forward to all the 100s I'm going to see on exam 3 and all the super high final exam grades too. I'll talk to you guys later.